Once we understand how to write electron configuration of atoms and ions, we find specific trends and patterns that explain why the periodic table is organized the way it is. The first couple of things to note is that the period number in the periodic table is really the same as the valence shell number. So if I look at the first period where you have both hydrogen and helium in it, the valence shell there is going to be the 1s shell, and so that's your first period. You go to the third period, for example, the valence shell for all of these elements in the third period, starting from sodium all the way to argon, is either going to be 3s or 3p, the valence orbitals, but all of those are still going to be in the n equals 3 shell, which means that the valence shell is going to be the third shell. So the third period corresponds to having a valence shell at level 3. Going back now to the next observation, and that is that the main group elements have the same number of valence electrons as their group number. So going back to the periodic table, if you remember, the main group are the first two groups and then the last 6 groups. Remember that group 1 is called group 1a, and if you go ahead and write electron configuration for all of these elements, you will find that all of them only have 1 valence electrons, and it's going to be in the s orbital. So hydrogen will be 1s1, lithium will be 2s1, sodium will be 3s1, and so on. You can go to another main group element, for example, the oxygen group, which is group 6a. If you do that electron configuration, you'll find that they all have 6 valence electrons. I'm showing the one for oxygen right here. Oxygen is period 2, group 6a. Its configuration is 1s2, 2s2, 2p4, and so if you add up the total of that valence electron, you get 6. And it's period 2, so the valence shell is equal to 2, as we just discussed. So both of those are really useful pieces of information because now it explains why those periods and those groups exist. Now here's the next one. We can divide the elements in the periodic table into groups that are based on where their last electrons are located in. If we look at the periodic table and write the electron configuration for every element in the periodic table, we will find that the first two groups, all the elements in here, will have their last electrons in the s orbital. So we would call these the s block elements. If we look at the other representative elements, which are the ones colored green, we will find that all of these elements will have their last electrons in the p orbitals. So we would call these the p block elements. The transition elements, we will find that all of them will have their last electrons in the d orbital. So we would call these the d block elements. And then the lanthanide and actinides, which are elements that follow lanthanum and actinium, they all have their last electrons in the f orbital. So we call these the f block elements. That makes it a little easier to write electron configuration for specific elements because we always know where the last electrons is going to be found in. Now here's a really important discovery that was made with the electron configuration. People have known for a long time that the noble gases are inert. They don't react with a lot of other elements. In fact, the first 3 noble gases don't react at all. The other noble gases will react, but then not by a whole lot. And the reason they don't react is because they are stable. The reason things react is because they want to lower their energy or make themselves more stable. The noble gases must be already stable so that they don't really need to react anymore. When we do the electron configuration for all the noble gases, we find that they have fully filled or complete s and p orbitals. Now I say ns here because I'm referring to the period that the noble gas exists in. So for example, if I'm looking at neon, that's period 2. So the 2s and the 2p orbitals are completely filled. If I'm looking at xenon, that's period 5. So the 5s and the 5p orbitals are completely filled for xenon, which means it will have the configuration of 5s2 and 5p6. Well, that's the only difference between the noble gas and everybody else. That must mean that having a fully filled or complete s and p orbitals of that given level or that given period make that element a lot more stable. Now, what this also means is that if an element wants to become more stable, what it would do is it would try to either gain or lose electrons in a way where its electron configuration becomes looking like the electron configuration of a noble gas that's closest to that element. So this actually explains why specific ions are formed by the representative elements. As I said, these elements either lose or gain electrons to complete their valence shell so they can look like a noble gas. Here are a couple examples. The sodium atom has 11 electrons, so its configuration using noble gas shortcut is neon 3s1. If you look at sodium right here, there are two noble gases that it could become, neon or it could become argon. Those are the two closest noble gas to it. Well, the one that's closer to it is neon, right? Because in order for sodium to become neon, it just needs to lose one electron. For sodium to become argon, it needs to gain 7 electrons. Since it's easier to lose one electron, we find that sodium tends to form the sodium plus ion, which means it's lost one electron. And the configuration of the sodium plus ion is just the same as the configuration of neon. Now, if we look at a different atom, chlorine in this case, chlorine has 17 electrons. The closest noble gas will be argon. Neon would be the next one. So to form argon, what chlorine needs to do is gain one electron. So we see that chlorine tends to form the chloride ion, or Cl-, where it has gained one electron to make it look like argon. So this is a really useful information because now we can understand why certain elements form specific type of ions. Now, what about the transition metals? Well, the transition metals are a little unique because if you remember, all of the transition metals, they have their last electrons in the d orbitals, but their valence electrons is actually not in the d orbitals, but in the s orbital that is neighboring to the d orbitals. So for example, for the elements in the fourth period, the valence electrons are in the 4s orbitals, but the 3d orbitals is the neighbor of the 4s orbital, and they are very similar in stability. What that means is that the valence electron, which is the ones that are furthest away from the nucleus, is the 4s. So if these elements want to form ions, they're going to lose those electrons first. But once they lose those two electrons, it turns out that they can also lose some number of the 3d electrons because the 3d electrons are close in stability to the 4s electrons. This gives rise to things like multiple charges, which we had talked about when we discussed nomenclature. For example, if you look at iron, it has 26 electrons. Its electron configuration is argon, followed by 4s2 and 3d6. So the valence shell here is 4. So it has those two valence electrons. So it's going to lose two of those to form an ion that has the stability of a noble gas. And we know that we see that ion, which is the iron 2 ion, Fe2+. However, because 3d orbitals are close in stability to the 4s orbital, iron can also lose electrons from the 3d orbitals, and in this case that's what causes iron to have other charges. So for example, the Fe3+ ion is just the iron ion that has lost the first two electrons here plus one of the electrons in the 3d orbital. The last point I want to make here about the periodic table and electron configuration is that there are certain exceptions for transition metals configuration. And this has to do with only two specific groups. The first group is the group that is headed by chromium, which is all of these elements down here. Given that it has this particular location, you would expect its electron configuration to be ns2 and n1d4, meaning that if it's on period 4, it will be 4s2, and then 4 minus 1 is going to be 3, so 3d4. But it turns out that the actual electron configuration for those elements is actually ns1 and n-1d5, meaning that if it's fourth period, it will be 4s1 and 3d5. So the example here is chromium itself, which is on period 4. So its configuration is argon, the noble gas closest to it, right? So here's chromium, argon is right here. So it's argon, 4s1 and 3d5. Another exception is where the group where copper is the first element, which is this group right here. So for that group, we expect this configuration, which is ns2 n minus 1 d9, but what we get is actually ns1 n minus 1 d10. So an example that I would pick here is silver, which is in period 5. So its configuration is actually 5s1 and 4d10. The reason for both of these is turns out that having the configuration in the way that I just described increases the stability of the elements in those groups.